With that, we need to start our final lesson. So, kudos to you all for sticking with it through the end of the day. I have saved the absolute best for last, using R as a bona fide GIS, which is super cool because you used to not always have that option available to you using R, but now in the last couple of years. There's been some really great packages developed, in particular the SF or Simple Features package that Jim and I were just talking about that really plays well with the tidyverse and really improves the entire experience of doing geospatial analysis in R. So we're only going to focus on vector data today. So if you've used GIS before, you know there's vector data and raster data. We don't have time for raster data, and quite honestly, the functionality for raster data has not quite been as easy to work with as with vector data in R. So it's one of the reasons I'm focusing on that. I'm going to show you how to import vector data and structure and what the structure is in R, understand how R stores that spatial data using the Simple Features package, and then we're going to do some very simple geospatial analyses with the SF package. And just an FYI, I, for many years, was using ArcMap, and there's absolutely nothing wrong with that software, but once the Simple Features package came online, I am now almost using R 100% of the time for geospatial analysis. So this is one of the great advantages of R, is that oftentimes there's, as they say, there's a package for that. And so in this case, this package works really well, and you can almost do your entire GIS workflow in R now. The exception being map making or cartography, which still involves a bit of a manual work to make the map look really good. And I think in ArcMap, it's still a little bit easier to do that. Either way, that's pretty much it for vector data in R. So if you've ever taken a GIS class, you know that there's 3 different types of vector data. So this is points, lines, and polygons. It's as simple as that. So 3 different types. Polygons are essentially lines that connect in a circle. Lines are collections of points, and points are just 2-dimensional, or rather 1-dimensional locations denoted by a X and Y value. So when you're working with any GIS data, you know, you got to understand what type of data you're working with, whether it's points, lines, or polygons. But that only defines the type of shapes you're working with. So there's also 2 other pieces of information that come with vector data, and this is the same in ArcMap as is in R as well. So there's attributes that can be associated with each feature. So a point or a line or a polygon can have an attribute that is descriptive of that feature, like size or some other like environmental characteristic that describes that feature. So there's attributes, and then there's a coordinate reference system, or CRS. And the coordinate reference system is really important because it not only establishes a frame of reference for the locations in your spatial data. So what does a UTM value of 2000 mean relative to what your CRS is, or what does a latitude and longitude decimal degree value mean relative to what CRS system? It's always in relation to something. So you need to know what that is, because when you're doing geospatial analysis, you need to make sure you're comparing apples to apples. So if I wanted to compare something that was measured in millimeters, just as an example, to something that was compared in or measured in centimeters, I wouldn't have any meaningful comparison because those things use 2 different units of measurement. It's the same thing for CRS. So you want to make sure that when you're combining layers or intersecting layers or joining layers, they have the same coordinate reference system. And so this is probably an example many of you have seen before if you've ever taken a GIS class, but This is essentially what a human head looks like with different projection systems. So this looks very odd to us. The same thing happens to continents on the map. And the reason it doesn't look so odd to us with continents is because we're not used to staring at continents all the time. When you look at a face, you can see how wildly stretched or out of proportion it is depending on what coordinate reference system you're looking at. So that's why a head is used as this example, but it applies to anything that is projected in three-dimensional space onto a two-dimensional surface. So to summarize, I mean, that's your quick GIS vector data 101 tutorial. Vector data includes three things, and I'm just wanting to remind you of this because this is important when we talk about how the SF package stores vector data when you use it in R. So there's spatial data that describes the coordinates, whether that's points, lines, or polygons. Then there's attributes that are attached to those coordinates or the spatial data. And there's a coordinate reference system. So those are the three things to keep in mind of. So enter the simple features package. So as I said before, GIS analysis in R is not a new thing. It's been around for quite some time. For many years, the SP package was quite popular, but then the SF package came along and it sort of revolutionized how spatial data are stored in R. And it actually, because of the way it stores the data, it plays really well with the tidyverse. And I said in the very beginning, the tidyverse has really propelled R into the next level with data scientists. And now that we have the SF package that links into that, it just makes geospatial analysis that much easier in R. So the simple features package follows the same data structure as I just mentioned for the spatial data. So there's points, lines, polygons, but you can also have these things called multi-points or multi-lines or multi-polygons. So think of, here's one line. This could be a river, right? And there could be like an attribute attributed to that or an attribute assigned to that river. But if we have a multi-line string, this could be like a collection of spatial objects that really only describes one entity. So a collection of streams that has one attribute. So just because the spatial coordinates or the spatial objects in this data set are not continuously together in space, they could still define one entity. So that's all we mean by multi-lines or multi-polygons or even a geometry collection, which is a mixture of all three. So that's just an important addition on top of what we already know about the way spatial data work in vector structures. All right, so for this exercise, really simple. I'll give you 5 minutes just to be fair, but we're just going to make sure that our packages are loaded. So we've been using the tidyverse all day, so you should have that. But now in this lesson, we're going to use the simple features and map view package. So you should have them installed. And remember, you only need to install things once, unless of course you reinstall R again. But every time you open R, you need to load them with the library function. So make sure they're installed, load these libraries, and then load the data we've been using on top of this data set, the seagrass data.shp. This is in the data folder that you should have that we've been using all day. And we'll use the stread function to import that. So I will be quiet, put 5 minutes on the clock, and let you guys sort out loading and installing SF.
Hey, Marcus, can you hear me?
Yeah.
Yeah, I can't figure out what's going on perhaps with his setup. Looks like he's getting the linear model lines in the MPG plots, but not in the fishstat plots for some reason. When
Okay.
Megan and I use his code, we're getting the desired results, but he's not getting them with his data sets.
Okay. Let's follow up with him afterwards, see if we can figure
Okay.
it out.
That's what I told him. I just wasn't sure if there was a simple thing that I might have been overlooking.
Yeah, if you guys can't get it, it's got to be something that is not obvious.
Gotcha. Thanks.
Yep. All right. So you should have been able to successfully load the packages and import the data. So I'll go to my live coding and I'll start a new section. Spatial analysis. Ta-da. Load SF. Map view. I believe tidyverse is already loaded, but I'll just do it anyway. Send it in. Okay. Good to go. Let's see, fishstat. Someone was asking about tab completion. So if you are looking for a particular data file in your working directory, you can press tab in between the quotes and get a list of things that might be there if you don't know exactly the file name. So there's data, and look, there's fishstat. So tab again, there we go. Same thing for stat loc, stat, there you go. And then sgdat, stread was the function from SF we needed for that. So that's, again, also in the data file. What's tricky about shapefiles is they are several different files together. So if you are going to import it into R, you would just use the .shp file extension there, and as opposed to the other ones. So there you go, it's in. Just curious if folks on cloud were able to do that. Let's see if I'm seeing something in the chat about it. Oh, it's refreshing. Okay. Okay, cool. Well, it looks like it is working for people on the cloud, so I'll just keep moving on. So that's it. The data are loaded. We're ready to go. All right, so there is a ton of methods available for simple features objects. So you should look at sgdat, look at the class. So this is basically R saying this object that we've imported is a simple features class. And it's also a data frame. So objects can have more than one class depending on the types of methods that are available for it. So if I go methods class equals SF, I can see all of the things that are available to me in the simple features package for the SF object class. So if you've done GIS before, this looks familiar. We have crop, filter, intersection, simplify, write if you want to save a file, get area, create buffers, get a bounding box. We'll use this one in a second, ST as SF. This is a function that lets you convert a data frame with coordinates to a SF object, which is pretty useful. But there's a lot of different stuff you'll see that is probably very similar to what you're used to doing for geospatial analysis. The reason that all of these functions are preceded by ST is a little weird because this is the simple features package, but this stands for spatial and temporal, and this is kind of a throwback to the old methods that are available in something called PostGIS, which is the old open source library that has actually served as the foundation for a lot of geoprocessing engines. I think Esri actually uses this too. So this ST prefix nomenclature is kind of a throwback to that. Not to mention, with finding functions, all you have to do is type SF into the console. I think if you do it in the script as well. So if you don't know what function you're looking for, this is a cool feature about RStudio. You can just type in the first couple of letters and you get a list of everything that is available. So yeah, here's other functions from other packages, but SF is the first one that pops up. So let's talk about this shapefile, what it is. This is a shapefile of seagrass coverage data for all of Tampa Bay, I think in 2016. So it is kind of a large file, but it's something we use a lot here at the estuary program, along with the other years of data that we have to track coverage over time is one of our assessment goals for the program. So we have this data set and we import it with STRead, and you get this in the console when you type sgdat into our console and press enter. So this says it's a simple feature collection with 575 features, so 575 individual polygons and 2 fields. So features are like rows, fields are like basically columns. These are the attributes. So this is a polygon collection, as I was saying, as one type of our vector data types. These are the dimensions, so X and Y coordinates only. There's no Z field for elevation. This is the bounding box, min max of X and Y, and this is the coordinate reference system. So WGS 84, which is like your standard geographic projection for lat long. And then this is the first 10 features that you see. So object ID, which is just a unique identifier for the polygon, and then a flux code, which defines the type of seagrass that you see in the polygon, where 9113 is patchy seagrass and 9116 is continuous or dense seagrass. And then we have this geometry column that is defining the spatial coordinates for each of these features. So this looks just like your standard data frame that you're used to, but now we have this geometry column that stores all of the spatial data that goes into this object. So the 3 parts I told you about for vector data is spatial data, that's the geometry, attributes, that's object ID and flux, and then CRS, the coordinate reference system. Those are the things to watch out for when you're working with vector data. So this just breaks down what I just told you. This is all metadata at the top. Each row is a feature. The red column is the geometry, and then the blue is the actual spatial data that applies to each polygon. So the actual points, the coordinates that make up that polygon. So that's how you would import a shapefile. But what if you don't have a shapefile? What if you want to create a spatial data object, a simple features object from data that you already have? Well, you can probably guess where this is going. We have our fish dat that we've been using before that has the catch data. And then we have our station location data that has the coordinates of each station. So looking at the structure of those data, you should be familiar with this by now, but this is the whole structure of fish data. This is the whole structure of station location. So you can imagine there's a couple steps we need to take before we make this a spatial object. So that's actually what I'm going to have you do in exercise 13, and we'll walk through this, so don't worry. But the function you're going to want to use is STSSF, which I just mentioned a second ago. But this function is going to be your workhorse for converting simple data frames to spatial objects. So the main argument is basically the data set you want to convert, and then which columns, you have to tell it which columns are the X and Y coordinates that define the spatial data. And you have to tell it what coordinate reference system you want to use. It's not always a safe assumption, but WGS84 is typically the most common one. If you're familiar with coordinate reference systems at all, they're a total beast to work with and to manage. And there's a lot to say about them. But there's some pretty simple workarounds we can use in R for using them. So again, we're going to take this function and create an object with the data, the spatial data, the attribute data, and then the CRS. So that's what I'm going to have you do in this next exercise. So we're going to first do a left join by the reference key to combine the fisheries data and the station data, and then use the STSSF function to make that a spatial data object. Now just follow these instructions and you should be able to do it. The shortcut is the CRS number here, 4326. That is an EPSG number that is a numerical way to define a coordinate reference system, and this is corresponding to WGS84. So I'll give you 5 minutes, and then we'll, like always, go over what we've done. All right, so a lot of discussion going on in the chat about coordinate reference systems. There's a lot to say about them. Hopefully some of these links up here will give you some guidance. If I had more time, I'd do my best to try to explain a little bit more about what they're, how to work with them in R. But again, they are kind of difficult to work with, but it's just kind of a necessary evil of working with any GIS data. So I just one real quick, I like to use these numbers, the EPSG number instead of the actual text string for WGS84, which is kind of a long, nasty thing. Looks like that, which I can't remember that every time, but I can remember 4326, so I just use that. The other point is this specifying the CRS and the call to ST as SF only tells it what the coordinate reference system is. So it's up to you. It's to do your due diligence to understand that the spatial data you have, the actual numeric values for Latin long, are actually in that reference system. Otherwise, you could have a projection that is incorrect. I'll talk about ST transform. That's another function in a second that lets you convert between coordinate reference systems, which can be really handy. And that to me is a huge advantage of using these functions in R. It's a lot quicker to do spatial transformations as opposed to doing that in ArcMap, for example. So hopefully that was a little clarifying, but in the interest of time, I am just going to copy and paste the answers and show you how we do that. So we imported these two in the last exercise. What are we on? 11? Who knows? So we can join them with the left join by that shared key. Reference is the station. So now we have all data. If you haven't figured this out, the way tables are printed, kind of like data frame, the way they're printed in the console is to truncate some of the output. So you can see the remaining columns down here. And so I can see that latitude and longitude are printed down there as well. So that worked. And then we need to use ST as SF to convert this to a spatial data object. So we give it our data, all data. We tell it what the coordinates are. In this case, it's XY, not YX. So longitude is the X variable, and then latitude is the Y variable, and then we give it what coordinate reference system it's in. So just for fun, I'm going to copy that, see if that was right. Yeah. So now it's a simple features object. Now it's telling me 2,800 features, 12 fields, and we should be good to go. So I wanted to stay on this topic a little bit about coordinate reference systems and how they're annoying but necessary. So there's a couple quick cheats you can use when you're specifying coordinate reference systems in R. There's the stcrs function, which tells you what the coordinate reference system is. So if we run that on our data object, st_crs all dat, we see that it is EPSG 4326, WGS84 datum, longitude, latitude. So good, that's great. But say, for example, we didn't know this text string, or we knew that this data object did have that projection, and we wanted to borrow that projection from another object. So we can look at stcrs, our seagrass data. What is that? Same thing. So we can do a little bit of a cheat, where if we wanted to create the object this way, stcrs sgdat, so we're taking the CRS, which is basically just a bunch of text, so R knows what it is. from another object and assigning it to this new object that we're creating. So again, just a quick workaround if you don't know the EPSG number or this super gnarly text string here. And then finally, yep, okay. We can also use ST transform that I just mentioned. So WGS84 is the most common projection I work with, or a geographic coordinate system, but oftentimes I often use the UTM, Universal or Universe Transverse Mercator projection, which is in meters, and this often works well for doing geospatial analysis because things are measured in meters and distances are easier to assess in that unit as opposed to decimal degrees. So that's just another one. You can use ST transform to do that. Of course, you have to have an existing CRS for this object to do that transformation. All right. So now that we know how to import data, how to create data, we're going to do a little bit of mapping and geospatial analysis. So the SF package has a plotting method that works out of the box with SF objects. So if we were to plot our newly created all-dat data set, you would see something like this. And by default, it creates a new plot for every single feature or every attribute in that data set and color codes them accordingly. This isn't necessarily all that useful, but it's a quick way to see what data you have, what the features are. Just be aware that if you have a data set with like dozens and dozens of attributes and you plot like this, it might break R. So this is usually not my first go-to. What I usually do, same thing for the seagrass data. So here's two attribute fields in the seagrass data, object ID, flux code. So this is, again, polygon data. This is point data. What I was just saying is what I usually do for plotting is you can plot just the geometry independent of the attributes. So again, if I wanted to do everything, I would do that. Actually, it'll be nice to you. It'll say I'm only going to do the first 9 of 12 attributes, so it won't try to plot everything. But another way, if I wanted to just plot the geometry, I could say st_geometry. This is a nice function that pulls out just the geometry, so the point column in that data set, and you could plot that instead, just to get an idea of where these places are in space. So that's a nice way to just quickly look at the locations of your data. You could do that for the seagrass too as well. Now, to further drive home the point that this is a great advance for geospatial analysis in R, I'm going to use some existing functions from the tidyverse that we learned about earlier in the day to do some quick wrangling of this data set and then plot it. So my all-dat object, remember, that's a simple features object. For all practical purposes, we can treat this like a data frame that you want to work with dplyr. So filter that we used before applies to this data set as it does to any data frame. So here I'm saying give me all of the rows where 2016 was the year. So in the whole data set we have many years, but maybe we just want to look at that year because this is the fish data and we have seagrass data for 2016. So maybe you want to compare the same years between the two, and that's why we're pulling that out. So there we go, and I want to plot the geometry of that as well. This is also shorthand, that dollar sign to pull out that column. I could have just as easily done st geometry filtdat, get the same thing. So obviously we have less points here because we've taken a subset of the data, but we still have the filtered data as an SF object. It retains all the attributes and spatial coordinates even after we've applied a filter. This might not sound like a big deal, but back in the old day, this was really hard to do in R. And we used pipe, so even better. Okay, so that's just quickly showing you how the tidyverse works with these simple features. We could use mutate, select, summarize even, which is really cool if you want to do that with spatial data objects. But now we're going to do some quick geospatial analyses. So we might ask ourselves, okay, well, we have with this fisheries data set, we have the seagrass data set. Maybe we want to know how many fish were caught where seagrass was observed in 2016 if we know that seagrass is an important habitat for a lot of different things. So to first get at this question, we want to know where these two data layers are co-located. So where the fish are and where the seagrass are at the same time. So we're going to use our filtered data set where we already pulled out 2016, the same year as the seagrass data. And now we're going to do a spatial join with the seagrass layer. So this is, again, another super simple step in R that takes a couple steps in other software, but we can basically say subset, all this is doing is saying subset all of the rows. This is almost like a filter. Subset all of the rows in this data set that are co-located with our seagrass data set. And again, both of these are simple features objects, so that's why this works. This doesn't work with data frames. But if we did that and assigned it to this new object called fish crop, so I'm cropping out the fish where seagrass are, just ignore that. That's just telling me that sometimes spatial coordinates are necessarily accurate in latitude and longitude. But if I can look at the cropped data, so I'm toggling back and forth between the two. So here's the filtered data, 2016 only. We have points in the middle of Old Tampa Bay. Going back to this one that's cropped, now we have points along the shore where seagrass usually grows. So we know this is right. We can even plot the two together to visually look at the overlay, which we'll do in a second. Now, let me just save this so you have it. So now, all we've done here is just a spatial join, or rather just a cropping of the fisheries data where the seagrass data is located. The data set we've created is still only fish data. We haven't really truly intersected the two data sets. We've intersected them in space, but we haven't intersected the attributes or the fields that are in each of the data sets. So there's another way to do that, and if you're, again, familiar with ArcMap, there's an intersect function that'll do that for you, but we can also do that in R with one simple step. So we can use the st intersection function, which we'll copy and paste here. So this is, again, really simple. It just says, let me intersect the all data with sgdat. In fact, I'm actually going to switch that to filtdat because that's the one that is 2016 fishdat only. So we run that. Again, we get some warnings that say, be careful, you're trying to do things with latitude and longitude that doesn't necessarily translate in two-dimensional space, but we don't get any errors. So we can just assume that it worked all right. So if we plot this one, it should look exactly the same as that plot I already have up, because it's the same spatial crop, but now we've combined the attributes. So you'll notice the plot didn't change. So if I toggle back to the last plot, it looks exactly the same. So the spatial clip is the same, Oops. Just copy that up so you guys have it. But now if we look at the data, fish intersect, now you can see that there's other attributes on there that is the combination of the two data sets. I'm actually going to just put that up here. So here's what our fisheries data looks like, but now we have, there's object ID, in this case .1, because there's already an object ID here for the fish data, but this is from the seagrass data. And then we have Flux code to tell you, oh, this is continuous seagrass where 11 pinfish were found. So super easy to do an intersection with the SF package. In a lot of ways, this is almost like like the joins we talked about earlier. All right, and we can, as I said earlier, it plays really nice with the tidyverse. So this example is just showing you that we can take this intersected data and get a quick summary of how many pinfish were caught for 2016 in the two different flux categories for seagrass, so patchy and continuous. So not only, this is using our group by summarize that I showed you earlier. So not only is it doing it on the attributes, it's also doing it on the spatial attributes as well, which is like, blows my mind sometimes that it can even do that. So super cool. That the fact that this plays really nice with some of the functions you're familiar with the tidyverse. And there we have a plot. Hooray. So we've got some groundbreaking results that shows essentially there's more pinfish where the seagrass is denser. So that's something we can write and publish and get famous. All right. So we're on the tail end here. I just, that is a quick tour of, geospatial analyses and how it integrates with some of the tools we learned about earlier today. But I want to close with, how do you make a plot of a map in R with the SF object? Again, in the past, this wasn't necessarily the easiest thing to do, but now that we have the SF package, plays really nice with ggplot. We have an SF geometry type that specifically plots objects that have the SF class. So I am going to show you how to do that one. So I believe if you load ggplot or the tidyverse, you don't have access to the SF geometry until you load the SF package. I could be wrong about that, but just be careful when you're trying to do this that you have both packages loaded, so ggplot and SF. So here I'm plotting the seagrass first, and again I'm going to change the second geometry to the intersected data so I can see the spatial overlay. So I'm just going to show you seagrass first. And it does take a second because there's actually a lot of data stored in the geometry column. So there's our seagrass. Let's just try something that we learned last time so we can map an aesthetic to the Flux code. I believe we can do that. Yep, Flux. So see how that looks. I'll have to, actually, I'm sorry, that'll be fill because it's not color because we're filling the polygon as opposed to changing the color of the line around it. So I'll have to make the aesthetic fill. So we'll plot that. I'll show you what that looks like. Okay, that doesn't exist. Flux with an S. Cool. So now you can see Dense seagrass is the blue, patchy is the coral, and then putting the intersected fisheries data on top of that. We can see those as points. So there you have it. Pretty simple with ggplot. It automatically converts the axes to lat and long and decimal degrees and behaves with the mapping aesthetics just as we discussed before. So this is a static map, which is fine for if you just want to look at something as a static map. But the map view package, which is the last thing we'll talk about today before we have our last exercise, is another really cool package that plays really nice with simple features objects. And so first thing you'll notice is that, hey, I can move this and I can zoom it around and I can mouse over points. I can even click on points and get data. So I just clicked on fisheries data point. I can click on the seagrass data and see what's there. So this map will be created with only 2 lines of code and really simple code. So let's do that real quick. So here's map view. Now this actually, I think I lied earlier when I said ggplot was the only thing that you string together with a plus sign. Map view, you do it the same way. So here I'm actually creating 2 layers over the base map. So I'm first, just like I did with the static plot, creating the seagrass. So that takes a second to render, and it pops up in the viewer tab. I talked about that way back this morning about how that could be used. This is where interactive stuff goes. So now we have seagrass there, and we can run that again by adding the fisheries data on there. And so change this again to the intersected data. And you'll see what this does in a second. This is kind of like the aesthetic mapping in ggplot, the Z call. This basically says map color to gear. So here we have only 2 gear types in our intersected data set, gear type 20 and gear type 160. But we see where those locations are. Again, we could click things and we can even zoom out of there. So I just hit that zoom button. You could do that for plots too, but we can make that much bigger. So there you go. Really cool. You have different base layers you can look at, satellite images. See the legend down here, the scale bar changing as you zoom in, zoom out. I believe, can you turn off layers? Actually, not. You can't do that with map view, but other plotting libraries and interactive, you can do that. But anyway, that's sort of your tour de force for map view. So a really cool feature to create quick interactive maps with simple features. So yeah, there's a lot more I could say about that, but you know, we've covered a lot of stuff, not only in this lesson but today. So we'll stop this lesson at the final exercise where I'll give you a chance to play around with this for yourself. So everything I just showed you, I want you to try to do on your own. So do that intersection of, well, you could do it with all data if you like, that includes all years, or you do it with the filtered data that's only 2016, but do the intersection and then create an interactive map with map view and try to map color to, map color to one of the attributes in your data set. And you can even get fancy if you have time to combine some of the maps, so the seagrass plus the points. So we'll put 5 minutes on the clock and we'll let you at it. All right, so that was our last exercise. Our intent was to blow your mind with what you can do with GIS and R, so hopefully sufficiently did that. There was one question in the chat about saving these things as HTML, so you can send them or view them in a web browser. This button here, show in new window. So I just popped that up. So this button right here in the viewer, if you hit that, it'll open up the viewer in your browser, your default browser. So if you know anything about web design or building web pages, this is a really easy way to link this content into a web page. But that, of course, is a whole other lecture. But I believe you could save this or print it or something like that as HTML, but I haven't explored that. So I use, for this website, I did this all in R Markdown, which is a way to integrate text with code, and it renders in HTML. So again, that's a whole other lecture, but it's with minimal training, I guess. We could teach you all how to make your own HTML files that you can share with others. That includes plots, code, text, and even interactive maps. So that could be something to look forward to in the future. So with this remaining time, I just want to wrap up a few items. Again, really want to thank you all for your attendance today and your continued patience and willingness to learn R today. This is, of course, just the beginning of your R journey. This was a huge amount of information for you guys today if you've never seen this before. So don't at all be discouraged if you're running into problems or having difficulties or just don't feel like you're not getting it. Just realize that's totally normal. And I always like to say that if you feel like you're spinning your wheels or struggling trying to solve a problem, then you're learning. So be stubborn. Always try to find an answer or a solution, even if it takes a little bit of time, because through that process, through that struggle, you are learning. Yeah, just stick with it. So we do have a couple resources for you. This website will stay online as long as the internet exists. So you can always go back to this as a resource. As the software continues to develop, some of these things will get outdated unless I update the website. But for the most part, most of this is still relevant and timely and used within our community widely. So you can always go back to it. If you again, remember, say in the future, you hear about some topic that you're not so sure about, but you remember hearing about it in this workshop, you can go to that section and read it for yourself and beef up on that. So again, this is just meant to be a resource where you can find things moving forward. On top of that, we have this data and resources tab. This is not just a collection of the data sets we've used today and the scripts, but I've tried to compile a list of resources that you can use for continued learning. All of these, actually some of the carpentry stuff you might have to pay for, but all of this stuff should be, aside from the data carpentry, free to access, especially these ebooks. So I've used R for data science a lot for this training, so I encourage you to check that out. You can go to that website, view all the content. Jenny Bryan, she's another big hitter in the R world. She is a great teacher, and all of her online content is very excellent for teaching advanced topics. So yeah, feel free to go through these. And also I had some stuff in R Basics too. I glossed over how to find help, getting help, but there's a lot to say about this as well, about some of these resources and even the art of Googling to find answers. So just stick with it. I like to think, I could always be a resource to the best of my abilities to you guys. So feel free to contact me directly if you have any specific questions about R, especially this workshop. If you thought this workshop was great, I'd love to hear that too. If you thought there were parts of the workshop that you thought could be improved to cater to different learning styles, or if there was other subjects that we thought we could have hit on, feel free to let me know that too. But by and large, I think we're done for the day. We have technically 8 minutes until 4 o'clock, so I can stay on the line and answer some questions live if you guys like. Otherwise, thank you all again for your time, and I hope you enjoyed this workshop, and there's more to come. Thank you all.